Hey everyone, today we are going to be doing a full implementation of language diffusion models, both for pre-training and supervised fine-tuning for question answering. So it's going to be awesome, but I want to give a little bit of a shout out first to this cool repository by Gumrin. Sorry if I mispronounced your name, but this is a even simpler implementation of doing language diffusion models. It was the inspiration for this implementation, so go ahead and please take a look at this and give them a star. And of course, the LADA repository, which is the main idea where most of all this stuff's coming from, because that's kind of what we'll be implementing. So let's talk about how diffusion is working for a language. Diffusion, if you take a look at my previous models on, or previous videos on diffusion, the entire idea is we take some signal, audio, video, images, whatever it may be, and we add some noise to it. And you train a neural network to essentially denoise it. But how does diffusion work exactly for language? Because language isn't a signal, it's discrete. We have some discrete tokens, which means it's a discrete diffusion problem. And our standard diffusion methods don't really apply here. So what do we do? How do we work with diffusion when we're not dealing with signals? And the way we do this is actually way simpler than standard diffusion, which is kind of cool to see. So the setup for diffusion will look like this. And maybe the best way to show this actually is through an example. So when we inference these diffusion models, inference, and this is kind of what we will be building up to. Let's see, bash inference.sh. This is what we'll be building up to. So we want essentially to start with a bunch of mask tokens and iteratively denoise, or predict what they are. This is the diffusion process for language modeling, where we again start with lots of mask tokens and quote unquote denoise them, but really just predict what they are. And so masked, or this diffusion language models actually isn't all that different from standard language modeling. It's no different from standard mass language modeling. So how is diffusion language models first different from standard language models that we've seen with Llama and GPT and all of that? The main difference is it's no longer autoregressive. So in standard language models, what do? We have some T1 and we predict T2. And then given T1 and T2, we predict T3. Given T1, T2, T3, we predict T4, ... We keep predicting until we predict a final EOS token. That's end of sentence, right? We're done with our prediction. And this is how every single language model, autoregressive language model, is trained. In diffusion language models, instead, we set up a kind of like a canvas, a bunch of these mask tokens, right? Mask tokens. And we iteratively denoise them, or essentially predict what these mask tokens are. What should they be? And what we're going to explore right now is a little bit of the derivation that goes into making this even happen. So the forward process, let's go back to the paper as we'll reference it as we go. Forward process is super duper simple. All we do is for every single sample in your batch, go ahead and select some t between 0 and 1. So uniformly sample it. And then with that probability, go ahead and mask out your different time steps in your data. So what this looks like is kind of like this. We have some tokens, let's say token 1, token 2, token 3, token 4. And I'm going to random sample some u. And let's say it'll come from a 0, 1, uniform 0, 1. And let's say I randomly sampled 0.3. That means about 30% of these tokens are selected to be masked. So let's say this one is about 25%, but that's fine. This is selected to be masked and everything else is fine. But we could have also sampled 0.5. Then 2 tokens would have been selected randomly to be masked. We could have also sampled 1, which means all tokens could have been selected to be masked. And so that's the key idea. Our training strategy is go ahead and first select some t, select some proportion with that, to select them to be masked. And then once they're masked, we go ahead and it's not as interesting when everything is masked. We pass it through some standard transformer, right? Nothing fancy, transformer. And then we predict what the masked positions were. Well, isn't this just mass language modeling? How is this different from BERT, Roberta, all the other stuff that we've looked at? And the thing is, it's not. It actually isn't all that different, except for one key thing. In masked language modeling, if you remember, we had a constant 15%. We had a constant 15% of tokens that were selected or candidates to be selected to be masked. And so that means in every single sample, we would randomly select 15% of those tokens, and those would be masked out. So in this case, in mass language modeling, it's constant. In our diffusion training, or at least pre-training here, it's no longer 15%. It can be anything between 0 and 100%. So you could have nothing masked, you could also have everything masked, and you could have anything in between. So that's one key change from our mass language modeling. Now, how does this make a diffusion process? Well, let's talk about the reverse process now. And the reverse process is actually a little bit more interesting because you can notice that there's actually something I haven't mentioned here. In diffusion, like when we train a diffusion model to generate images, we have big T. How many time steps, right? Time steps of noise, right? So we start with an image and we noise it, right, to a noisier image, and then noise it to a noisier image, noise it to a noisier image, dot, 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 until we get to the end. And a hyperparameter I have ahead of time is how many steps of noise do I want? Typically in diffusion models, it'll be about 1,000, right? 1,000 steps of noise. I didn't mention that here. We don't have that. So what does the denoising process look like exactly? Well, let's look at the paper first, and then we'll implement a very simple formula of where it came from. What they do is we start, right? So R1 is a fully masked sequence of length L, whatever it may be. And what we do is for every single masked position, which in this case is all of them, we go ahead and predict what should they be. Now, of course, at the beginning of our diffusion process, when you start with all masked tokens, the model doesn't really know what they should be because it's all masked. There's nothing there to predict. And so we're going to predict something. See, R0 is argmax. Go ahead and predict a token for each of those masked positions. But then what we're going to do is with probability S over T, we remask the data back. And that's the key idea. So let's go ahead and kind of set this up like this. We're going to have some fully masked we're going to have all masked tokens. And all of this is going to go through some transformer, some encoder transformer. And then we're going to predict essentially something like this. We're going to predict tokens for each one of them. T1, T2, the model will have some prediction for everything. T3, T4, T5, whatever they may be. But then what we're going to do is with some probability S over T, we're going to remask stuff, reset them back to masked tokens. Again, pass it through that same transformer, right? Same transformer as before. It'll go through. And then again, for these masked positions, I'm going to predict whatever they should be, T4. And then again, we're going to remask something. And then it'll go through that transformer again. We repeat this over and over again for however many steps we want. So what is S and T? How does this all work together? Where did S over T come from? That's basically the question that I want to answer right now. So let's start from the beginning. We have, let's say this, we first will sample some, let's say some U from a uniform 0, 1, and let's just say we picked 0.2. That means in our T1, T2, 3, 3, dot, 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 T n, however many things, or they use L, so we'll do L here. For each one of these steps, time steps in our data, we will randomly select 20% of them to be masked. Let's say this one and this one are selected to be masked. And that's it. So the probability, so I'm going to write it this way, XUI, this is their notation, so XUI, where U is basically our probability threshold, right? The threshold, or the noising threshold. What proportion of my data do I want to mask out? This is going to be, and it's going to be for some ith token, right? So for ith time step, this is going to be either V, which is, the original word, but that's fine, V, if some tau I less than, or greater than U. And then it's going to be a mask token if tau I less than U, which makes sense. If I sample 0.2, that means if I have a value, if I randomly sample some between 0 and 1 here, and then 0 and 1 here, 0 and 1 here, 0 and 1 here, I'll randomly sample a value for each one of these between 0 and 1. If we're less than 0.2, then it's selected to be masked. If we're greater than 0.2, then it's not selected to be masked because I want it to mask 20% of the time and leave it alone 80% of the time. So we'll replace the mass token when it's less than when it's basically in that noise threshold we wanted, and we'll leave it alone when it's greater. And as u becomes bigger and bigger, if u is 1, for example, that means, well, everything between 0 and 1 is less than 1, so everything would be masked. If u was 0, well, everything between 0 and 1 is greater than 0, so then everything would be the original word. And then we have all the possibilities in between. And so this is the question I now want to present, and what the paper essentially does. We have this system, and this is essentially just a Bernoulli random variable, right? Nothing fancy. So the question is this: what is QS given T, where we have XSI given XTI? So T is some noise level. S is another noise level, but S is less than T, because we're denoising, right? We're going to start with a higher noise level and go to a lesser noise level. So that's one key idea that we have to keep in mind. S is less than T, but what is this probability? And how granular we want it is completely up to us. In the case of a, let's say we have all these values between 0 and 1. If we pick noise, basically 10 steps, let's say we pick 10 steps, then we're going to go from 1 to 0.9 to 0.8 to 0.7. So in this case, T would be 1, and then S would be 0.9. In the next step, T would be 0.9, S would be 0.8. In the next step, T would be 0.8, S would be 0.7, ... We just repeat this over and over and over again. But if we pick 100 levels, then we go from 1 to 0.99, 0.99 to 0.98, 0.98 to 0.97. So these are the different noise levels that we could possibly be at. And so that's the way you can think about it. Our denoising isn't like a specific number of steps, but it's rather reducing the noise level from 1 to 0 in as many increments as I want. So big T is now basically an inference time hyperparameter. We'll see what that looks like in a bit. And so now that we have this, we can go ahead and set it up. So we understand what S and T are. So let's just derive what this should be. It's pretty straightforward. So XT I equals M implies that tau I was less than T, or this, my bet, should be an X. What does this mean? The probability of the ith token at noise level T being equal to M is the same as saying my generated noise, like some value between 0 and 1, is less than T. And this is again for the same reason as we had up here. We generated some tau I for each one of these things between 0 and 1 for every single time step, 0, 1, 0 to 1, 0 to 1, 0 to 1, uniformly. And then if it was less than 0.2, which is my U, or T, whatever it may be, if it's less than 0.2, then it's selected to be masked. If it's greater than 0.2, then it's not selected to be masked. And so if I had, at noise level T, if the ith time step was a mask token, then the tau I had sampled at that time step must have been less than T. Otherwise, no other way. And the probability of tau I less than T, well, that's just equal to T, right? Because again, let's say T was 0.5. So if tau I can be any value between 0 and 1, then what is the probability that tau I is less than 0.5? Well, because it's uniform, that would just be 0.5, right? That's it. That's all that's there. So in the exact same way, sorry, my handwriting got a little slanted. Let me fix that. So in the exact same way, let's go ahead and keep going. We want the probability of XSI equals M given XTI equals M. This is our remasking probability. It's asking if at the tth time, or at the tth noise level, if a token at time step I was selected to be masked, what is the probability that at the S noise level, at that same time step, it was also selected to be masked? And that's our remasking probability. With what likelihood should we remask a mask token in the next noise level? And so this is going to be probability of, and we know what each of these are. We know this is, if at Si it was M, then that must have been at tau I is less than S, right? And then this, for the same reason, is tau I less than T, right? That came from right here, right? So we know that if at the S noise level, if we had a mask token, then the tau I that we predicted or sampled for that ith time step, it must have been less than the s. Otherwise, it wouldn't be a mass token. And the same thing for t. If we sampled some tau I at the ith time step or ith token, and it was less than t, then that's the only way it would have been a mass token. And we're just looking for this probability here. And so this is the same as writing tau I less than s given tau I less than t. And this is pretty easy. It's just a joint distribution, or it's a conditional distribution. So we know the probability of A given B is probability of A and B divided by probability of B. So let's just do that. That's going to be probability of tau I less than S and tau I less than T divided by the probability of tau I less than T. Okay? Well, can we say anything about this joint distribution? If we had a number line, let's say, and we know that this is S and this is T, because I know for sure S is less than T. That's one of my restrictions. S must be less than T. I want the probability of this region and the probability of this region. Well, and means we only care about the overlap. And so the probability of something being less than S and less than T, given that S is less than T, is just the probability of less than S, right? It's just this region here, so it's less than S. So we can rewrite this very simply as just the probability of tau I less than S divided by probability of tau I less than T, just like that. And like I said before, this is just S over T, and that's where the S over T comes from, right? It's a very, very simple derivation here. And so there's not much going on. And here we go. So that's where this S over T comes from. And we just repeat this over and over again through all of those noise levels until we're done. That's step one. Now there's two other things we have to keep in mind when we kind of keep going here. So we talked about how we mask, we unmask. Okay, good. So let's set this up for one more thing. We have a question answer pair. In pre-training, you just train on data and there's nothing else going on. But now we have questions and answers. So this is going to be conditional masking. How we do this is we essentially provide a prompt. So this will be prompt token 1, prompt token 2, prompt token 3, prompt token 4. Let's say that's our prompt tokens. And then we're going to have our answer tokens. This will be answer token 1, answer token 2, answer token 3, answer token 4. In the way that LADA trains, when we do fine-tuning, supervised fine-tuning, we only do this entire masking strategy, randomly select a mask and all that, on the answer tokens alone. We never mask prompt tokens. We want our output here, the unmasked tokens, or our model. We want our model to learn to unmask these tokens given some condition, right? So it wouldn't make sense to hide the condition, so we don't. The condition is never masked, and we only mask and unmask, basically learn to unmask our answer tokens, given the condition. So that's the only difference that we're going to have from training or pre-training and supervised fine-tuning. That's one thing. Here's the other problem. Different questions need different answers, right? Different lengths of answers. Some answers can be short, some answers can be really long. How do we do that here? How do we control the length of our answers? Well, we actually can't, not directly. Let's kind of review how autoregressive models do this. Autoregressive models, you give it some prompt, right? So you'll give it, I'll just keep it short. We'll have some prompt, right? Some prompt tokens. And then we start generating autoregressively answer tokens. We're going to generate token answer 1, right? Answer token 1. And then, so given the prompt, we generate answer token 1. Given the prompt and answer token 1, we generate answer token 2. Given prompt, answer token 1 and 2, we generate answer token 3. And we keep doing this until we generate an EOS token as we're done. There's nothing left to generate here, right? And so that's essentially how it's set up. We just generate until the model generates EOS token, and that tells me that, oh, we're done generating. I'm done. I don't need to do anything else. But in my case, it doesn't actually work out that way, right? Because I don't have answered tokens I'm not generating autoregressively. I just go ahead and provide a bunch of mask tokens. We're going to have our prompt, and we're going to provide just a bunch of these mask tokens, right? Mask tokens. dot dot dot. Right? I'll have lots of them. But if I ask a question like, what is the capital of Paris? Or what's the capital of France? Right? Capital of France. Capital of France is my input. That's terrible. Let me write that again. France. Well, how many tokens do I need to answer that? I mean, how many tokens can Paris possibly be? I don't need the entire context length worth of tokens. And that's the problem. How do we do variable length predictions when we essentially are just predicting these mass tokens every time? And the way we do this is by actually learning a trainable pad token. And so what we do is the model, we hope it ends up learning that it'll learn like token 1, token 2, token 3, whatever it may be. But then it's just going to have all these extra pad tokens at the end. Extra pad tokens at the end. And so our model, what we do is we actually train on the pad tokens. And this is one key difference from mass language modeling. If you remember in mass language modeling, we'll have like a some sentence with some tokens, token 2, token 3. Then we'll have another sentence in the batch token, let's say token 1, token 2, token 3, token 4, token 5. We'll have another one, token 1, token 2. And what we do is we add on these extra pad tokens, right? Extra pad tokens to fill in the matrix, right? And during our transformer, we have this attention mask that tells us attend to the first 3 tokens, but ignore these last 2 because they're pad tokens. Attend to all of these tokens because there's no pad tokens there. Attend to these tokens and ignore these pad tokens here. And then our model just trains to attend, is trained to ignore, or not trained, but we essentially ignore these with our attention masking, right? In attention masking, we set them to -infinity, softmax zeroes them out, and so they have no effect in our final operation. And so that's all well and good, but in our case, we actually want the model to train to predict these pad tokens. Because the pad tokens, if it learns to understand that after these 2 tokens, these are kind of just our essentially end of sentence tokens, then during inference time, it can do exactly the same thing. It can essentially do a bunch of predictions, and for the tokens that it doesn't feel like it needs, it can just predict pad tokens and we can ignore them. So we have our actual data, but then all these pad tokens that are predicted that we can ignore, and they act as that end of sentence. So this is why a LDM is still able to do variable length answers. And just going back to here again, if we go ahead and generate stuff, notice how many mass tokens we start with. Basically the model doesn't feel like it needs all those mass tokens. So it can go ahead and remove the ones that it doesn't need and just keep the positions for the tokens that it does need. And so this is exactly what's happening. It's predicting pad tokens for these mass tokens disappearing here. And so because it's a pad token, I just don't visualize it because we don't really care about pad tokens. And so there we go. That's the entire setup essentially for LDMs. We have 2 stages. We'll have pre-training and fine-tuning. Pre-training is just train exactly how I said, just randomly sample some tokens, mask them out, predict what they are on the other end. No different from standard mass language modeling. It's just instead of doing only mass language modeling, we have a variable percentage of things we masked rather than just a constant 15%. And during inference time, just do exactly as defined. We start with all mass tokens, and then we basically predict all of them, and then we remask them, and then we predict and remask, predict and remask. And the probability of remasking a token, as we saw, is S over T, just as described by the paper. And then lastly, when we're doing supervised fine-tuning, we do everything exactly the same way, but we only go ahead and mask out answer tokens. We want our model to learn to generate answer tokens given the condition of the prompt, right? So that's the other difference. So let's go ahead and start building all of this out. Now to build this, as you can imagine, LADA is a llama-sized model. It is 8 billion parameters or something along those lines, which would be kind of hard to reproduce myself because I don't have that many GPUs lying around. So instead, we're going to go ahead and fine-tune an existing mass language modeling model, which is completely fair actually, because our models are all any model that can do mass language modeling is already good at predicting, well, mass positions, right? So there's really not a lot here for us to have to do. So we can use an existing mass language model. Now to do this, there is a couple of caveats. The model I initially thought about using was just Roberta, just like we had done in our previous videos where we kind of built Roberta from scratch. I'll link that down below if you want to learn more about how to build this model, pre-train it, and stuff like that. Roberta has one small issue, and that comes down to the context length. I'm not actually sure what it's defined, but I'm sure it's in here somewhere. Roberta has a maximum context length of 512 tokens. That's not that long, actually. Especially for question answering, you typically need at least like 1024 or something like that. So if we want to do Q&A kinds of setup for supervised fine-tuning, well, and here we go. So yeah, it defaults to 512. So our Roberta model only has 512 token length that it supports. So I needed a model that was longer in context length, but not some ridiculous multi-billion parameter size, just because I didn't want to deal with all of that. So the coolest model to use was ModernBert, right? So ModernBert is a model that came out a bit ago, and you can see it right here. ModernBert is awesome because it's a significantly bigger model. So it's almost 400 million parameters, maybe a little bit over for the ModernBert large. But it's still a reasonable thing to train. It's not some ridiculously large model with billions of parameters. The other benefits of ModernBert is it has a context length of just over 8,000, so it has a larger context length that we can use. It also does a bunch of other cool tricks. You can go ahead and look at the paper. It has some efficient attention mechanisms and stuff like that. It uses not just global attention, but also sliding window attention and all sorts of cool things. It has rope embeddings. So there's all sorts of things going for the ModernBert architecture that makes it really nice to use. So what we're going to do is basically fine-tune the ModernBert architecture here on our mass language or on our language diffusion modeling task. And you could use any model. You could go and use Roberta or anything else you want. It doesn't matter. You could use DistilBert. I believe that's what the Gumrin implementation did. Use DistilBert or DistilRoberta, something like that. So you can play with that. And you can do toy experiments, but I'm just going to go ahead and implement the full-blown implementation here, just because, well, why not? We're already here, so we might as well do it. There are a couple things we need to keep in mind, though, when we actually train this model. So the first one is that the model we're using, like BERT or Roberta or ModernBert, whatever it may be, it doesn't actually have all the tokens we need. ModernBert is for mass language modeling. It's not for generating like answers to questions, which means we need to add a couple things to it. So we need to update its tokenizer. So we're going to create a tokenizer first, and then we'll start writing the actual architecture itself, or really just training. There's really no architecture to write here. So from tokenizer.processors, import, let's see, template processing. And let's go ahead and cd to it. Tokenizer. Tokenizer is not a, tokenizers, my bad. Good, all right, so we're good. I had to do a bunch of reinstalls yesterday, so hopefully all the packages we need are still in here. Transformers, import the auto tokenizer. Right, so we're just gonna take an existing tokenizer and add a couple extra tokens to it. So we're gonna do def get tokenizer, model name, whatever model you want to use. I am again doing the answer.ai ModernBert base. And then we're going to have our beginning of sentence token. This is going to be BOS, end of sentence token. This is going to be our EOS token. So we're just going to add a couple tokens that it doesn't normally have, because I believe it only has like the pad tokens and the, what do you call it? Yeah, it just has the pad token and then like the start of sentence token. And so we could reuse the pad token that already exists in the tokenizer, but it's easier just to have our own, because in the implementation, it makes sure that the pad token doesn't ever get any gradients, and that's just annoying to deal with. So instead of kind of messing with the model itself, we're just going to add an extra token onto it, and that'll act as our pad token. And then we're going to have a start token. This will be basically our start ID. So we're going to see when we do our chat template, we're going to have some IDs like our this is the assistant, or this is the user, or whatever. So we need a start and end token for that. End token end token. This will be end ID. Oh, end ID. And then lastly, we have our end of text token. This will be the actual end. This will be EOT ID. And you'll see where all of this plays in just a second. So our tokenizer is going to be the standard auto tokenizer dot from pretrained, and it'll be that model name. So let's do if name is main. Oops. There we go. We're going to do get tokenizer, and everything else can be left default. So we can just print stuff out as we go. There we go. All right, now we're going. All right, so we have all of these we have these tokens, right? So we have the CLS token, which acts as essentially the start of sentence. We have a separation token, mass token. We're gonna need this mass token, so we're gonna use that one. But everything else, we could use them, but it's easier just to, add some extra tokens ourselves and just go with it. So it makes it, Hugging Face makes it very easy to just add tokens. We're gonna do special tokens. It's going to be, and there's a standard set of special tokens, like BOS token will be the BOS token. Okay. Oh, can't type. Fix this. All right, there you go. We have our end of sentence token. This will be our EOS token. We will have now a bunch of additional special tokens, right? We're going to just add on a couple more. And this will just be our list of our start token, end token, EOT token. So there we go. Those are all of our special tokens that we're going to be adding on. And so we can do our tokenizer.add special tokens, special tokens. And so if we print out our tokenizer now, tokenizer, we will see that we have all of these extra tokens, BOS, EOS, start ID, end ID, EOT ID, they've all been added in. Now they're in our tokenizer, but they're not in our models embedding. So we're gonna have to resize those embeddings, but we can do that when we actually write the training script, so that's no problem. So we're good there. What we're gonna do is set the tokenizer.pad token to the EOS token. And we're gonna set the tokenizer.cls token to the beginning of sentence token, right? Just so we don't really ever have that pad token or CLS token anymore because we don't need it anymore. And so the first step is a simple template processor. So template processors work like this. We can do tokenizer.tokenizer. So we're going to grab the object inside it, and we're going to change the post processor. If you ever wondered, how does Hugging Face just like take a tokenizer, you give it raw text, but it throws those special tokens in there anyway? And that's because they do something called template processing. And template processings are very simple. We only need to write it for the single example. You could also do it for pairs, but we don't really have that right now. So we're going to do, we're going to pass in the BOS token. Then it gets the actual, well, the sentence, right, the data. And then it gets the EOS token, right? We want to make sure everything starts with BOS and ends with an EOS. Simple as that. And all we need to do is just tell it that our basically BOS token is our tokenizer.BOS token ID. And you have to give these as tuples, I believe. So let's pass these in. And then our EOS token is again tokenizer.EOS token ID, just like that. So this is just going to take some sentence, tokenize it, and then make sure we put a BOS and EOS around it. And that's it. Now this kind of handles our first step. So let's do a quick method here. Test tokenizer, just so we can see what's going on. Our toke pre is equal to the get tokenizer. And I need to, yeah, this should be fine. Just get tokenizer. There's nothing to really do here. And we need to actually return the tokenizer here. Tokenizer. And there's no need to call it anything fancy. We can just do this. Okay, let's do actually not get, but test tokenizer. And we should be good. Okay, there's our tokenizer. So let's just create some text. I don't know. Full world, whatever. And so we can do our IDs is going to be equal to Tokenizer. And we're going to pass into it our text with padding equals true. Return tensors is PT. And let's just grab the input IDs and just index for that 0th sample, because that's all there is, print IDs. And you'll see that we've basically just added a bunch of stuff. So we have, oh, did I miss something? We have pretrained tokenizer fast, batch encode plus, return tensors. There we go. Oh, wow, I cannot spell. Return, there we go. Oh, okay, there we go. So there's our hello world. But you can see that we have a token before it and a token after it. And that's essentially our BOS token, EOS token that we put there. And just as more evidence, we can just go backwards, right? So we can do decoded is equal to tokenizer.decode. We can provide the IDs, and then skip special tokens is false, right? We want to actually see those. And so now we can do print decoded, and you'll see that we have, there you go. We have our BOS token, hello world, EOS token. So we're good. That covers our first set. Now, the other thing we need to do is a tokenizer for chat, right? We will be providing a input sentence or input prompt, and we'll be outputting a set of tokens. And so most chat templates are set up kind of like this. We'll do messages is going to be a list, and it's kind of like a dictionary. Like we have the role, and the role is a user, and then we have the content. And that's going to be like, what is the capital of France, right? And then after that, we have the second one, which will be the role. Role. It'll be the assistant, right? The assistant is answering back. And then the content is going to be Paris, right? Paris. Be a comma right there. There we go. So that's our standard. It's kind of like a dictionary, right? A list of dictionaries. And that's essentially how every single chat template, at least for Hugging Face, is set up. And so we just need a way to process this. Unfortunately, or not unfortunately, but by the purpose of the modern base architecture and most of these mass language models, there is no chat template in them, because why would there be a chat template in them? They're not meant for chat, but we need to add that chat template in. I'm going to go ahead and just copy paste this in, because this is always a little bit annoying to type. But the chat template is very simple. They're always set up like this, and it looks fancy, but it's really not. It's just some, I forgot the exact thing. It's called like Jira or something like that. But the idea is for every message and message, that's going to loop through each one of these things. So for every message and messages, we're going to do the BOS token if loop.first. So the very first thing at the very beginning, earlier, there has to be a BOS token. And then we're going to have a start token, which is basically this start token here, right? That's the start of an ID, like user. And we want the message role. So it's going to be start ID, user, end ID. And that tells me the start and end of like who's talking here. Well, it's the user person that's talking here. And then we're going to get the message content, right? The actual content of the message. And then similarly, we're going to have a end of EOT token. So that's like the end of turn. End of turn, because this is the end of the user speaking. Now it's time for the assistant to say something. So that's end of turn. And we're going to go ahead and grab that. And so we end for. And then if we add the generation prompt, right? So we have a flag. We'll see what that looks like in a bit. If add generation prompt is in it, then that's going to go ahead and add the start token, the assistant, and end token, right? So that's going to be the start of, that's the start ID. The assistant's the person we're talking about here, and the end ID. And that goes ahead and does that. So a little bit nitpicky, but that's basically how these chat templates are written. You could also just, I'm sure you could write a method that does it manually, but this seems easier, so we just did it this way. And so we can do encoded is going to be our tokenizer dot apply chat template. And we're going to pass in the messages. We're going to do tokenize is true. And then our add special tokens is also true. Print encoded. let's see here. All right, so there is all of our setup, right? That it's really as simple as that, right? We can see we have our start token and end token, EOS, or BOS and EOS, but then we also have a start ID, end ID, and then we have another start ID, end ID, wherever it is. So here, start ID, end ID. So that's it. That's our entire setup. Nothing too crazy. It gives us this, and actually just to make it a little bit clear, we can do our decoded is going to be our, again, tokenizer.decode. We're going to decode the encoded, and we're going to do skip special tokens is false, right? False. Oh, I need to print it. Print decoded so we can see. It's exactly what you think. We have BOS token, start ID, user, end ID. What is the capital of France? End of turn ID. Start ID, assistant, end ID. Paris, end of sentence. And that's it. And of course, this is just for training purposes, right? During training, we need this, but we also need one for generation. So how this will work is something like this. If we only have, and I'll just copy this in, right? And this is what that extra flag is for. Tokenizer. So if we have messages, role, user, content, who wrote Hamlet. This is me just asking a question, like what is the capital of France? Who wrote Hamlet, ... Well, I wanted to tokenize, I wanted to add those special tokens in, but I also wanted to add the generation prompt because the decoded then looks kind of like this. So we have decoded, decoded will be our encoded, print decoded. It'll look like this. So it's going to be BOS, start ID, user, end ID, who wrote Hamlet, end of turn ID. We have start ID, assistant, end ID, and now the assistant is going to pick up from here and start generating. And so that's how we're going to use it during inference mode. And so this is essentially the tokenizer that we're going to be using for everything going forward. So it's just because our standard mass language modeling is missing a couple of these kinds of features, we needed to just add them in, and Hugging Face Tokenizers makes it very, very simple to actually do that. So that's awesome. All right. So now that we have that, we need to prepare data. I'm going to kind of go over this stuff pretty quickly because it's not that interesting. So we can go prepare data. I'm going to delete that. It's the old one. I'm just going to copy it in because there's nothing of that much interest here, and that's not why y'all are here to look. So this is just using standard Hugging Face stuff. We're going to use our tokenizer. So that's the method we wrote, right? Get tokenizer. Use our tokenizer. Go ahead and just grab some data. We have some test split percentage. What's the context length? I get to do nice context lengths of 1024 now, just because ModernBert supports it. We have our path to data store. We have our Hugging Face cache. Where do you want to save? Where do you want Hugging Face to cache its processing? We have our seed for splitting, number of workers for processing, model name, all that stuff. So we have everything here, no problem. And then for training purposes, so the model I trained was on a much larger data set, about 40 billion tokens, though the model was very undertrained. I should have trained it for at least like a week or so, but I only trained it for 2 days, but that's fine. But we go ahead and train it, and we can see that it's essentially, I'm grabbing a 10 billion token split from FineWeb, a 10 billion token split from FineWeb edu, and then the Wikipedia corpus, just to get some variety in there. If you don't know what FineWeb is, by the way, it's an incredibly large data set from Hugging Face. I think the full data set is, 100 terabytes. So 100 terabytes, a absolutely gigantic data set. And then FineWeb edu is just a smaller split of this data set, essentially on like educational content. So I thought it'd be fun. I've never trained on these data sets, so I thought it'd be fun to just do that. And so we can go ahead, you can see each of these data sets just have this text column. That's the only column we care about. So we filter out all of the columns that aren't text, concatenate them together. If we are training on a data set that's one train on a slightly smaller data set, you can go ahead and use like Project Gutenberg or anything else. You can pick your data set, it's up to you. Go ahead and train, test, split it, and then we just simply tokenize all our text. And this is tokenizing with our pre-training tokenizer, right? There's no chat template or anything here. We'll write another data processor for SFT a little bit later. So we'll see what that looks like, but it's very simple. Go ahead and tokenize all the text and then loop through them, right? So loop through all the samples and then loop through context length words. So for example, if one of our samples is 4,500 tokens and our context length is 1,000, then we're going to grab the first 1,000, the second 1,000, the third 1,000, and then the fourth 1,000, and then we're going to have 500 leftover tokens. If that chunk that we grabbed is less than the context length, just go ahead and pad it with all of those pad tokens, and there we go. We now have some pad tokens in there. The official way of doing this, actually, if we take a look at the where'd it go? Okay, let me just reopen it again. Lotta paper. In the original Lotta paper, what they do for pre-training is they always keep the sequence length 4096. So that's the context length they trained on. We're just doing 1024, but that's fine. Where was the, here we go. They always train on sequences of 4096, but like we talked about, that pad token needs to be at least pre-initialized because it's more important when you do SFT, where we want variable length answers. And so what they do is 1% of the time, they'll randomly sample a sequence of some length between 1 and 4096, and then the model has to predict the pad tokens for that. So that's fine. We're not going to worry about that. We're just going to go ahead and just train like normal and just pad the extra things that are too long, and that should be close enough. It's no problem. And we can go ahead and save that data set right here. So let's go ahead and just see what this looks like, right? Just what this data set looks like. Really quick, should be very standard. So bash, we're doing the prepare pretrain.sh. So I'm not going to not found. Let me just do here, update it right here. There we go. All right, so yeah, there's just a mistake in the path. I think it's loading it, that's fine. It will take just a second. It's about 40 billion tokens is my guess. I think that's what the napkin math was for it, so I'll let it load. But it should print out. Yeah, it'll print out. So we can see what the data set looks like. We have basically all of these samples, about what, 1, 2, 3, 1, 2, 3. We have about 42.8 million samples that are each a context length of 1024, and then we have all of these validation cases. And we just have input IDs, right, for each of those sequences. And this is just a standard pre-training data, right? Nothing fancy. And so now that we have that, let's go ahead and actually write the pre-training script. So we're going to do, here we go. We're going to do pre-train, what do I want to call it? .py, that's fine. And like always, I'll just copy in the arg parse just so I'm not boring you with that, but it's standard training stuff. I think I just copy pasted my Roberta tutorial basically to do this. We don't care about bits and bytes, so that can go away. Okay, good. So we have all of this. We have basically experiment name, working directory, the model we want to use. In our case, it'll be the ModernBert model. Where's your data, the number of workers, your batch size, grained accumulations, training steps, you know, standard stuff. Nothing new, just normal training stuff. And so args is going to be equal to parse args. And then we're going to do path to experiment. It's going to be os.path.join. It's going to be args.working directory and args.experiment name, right? So that's where we're going to store everything. And accelerator is going to be the accelerator. Project directory is going to be the path to experiment. And then we're going to log with weights and biases. If args.log weights and biases, else none. Right, we're not going to log with anything otherwise. And we're going to do if args.log weights and biases, then we can do accelerator.init trackers args.experiment name, just like that. So nothing fancy. So step one, we're going to get our tokenizer, which is easy. We can just do our tokenizer is going to be tokenizer is get tokenizer, and we're just going to pass it args.href model name. Because again, the method we wrote here to update our tokenizer is generic, right? We did it on the ModernBert, but of course it can be done on anything, right? It doesn't matter. So there we go. That's our tokenizer. Go back right here. And now that we have our tokenizer, we added some tokens, right? We added extra tokens that our model doesn't currently have. So we need to add those in. So we're going to load our model. And we're going to do model is equal to auto model for masked, right? We're grabbing a standard masked language model dot from pretrain args.hf model name. So we're going to load that model, but we need to do model.resize token embeddings len tokenizer. This is going to go ahead and just resize. It's essentially going to add a couple of extra slots in our embeddings and pre-initialize them with something meaningful. There's some rules around, you could do like the mean or something like that, but it's going to go ahead and just grab those tokens and prep them. And so we now have some extra tokens in our embeddings for the stuff that we want to do. And so now we're going to do model parameters is going to be, we can see lambda p, we're going to do p dot requires grad model dot parameters, right? And what we're going to do is we're going to do params is the sum of p. We can do np dot prod p dot size for p in model parameters, right? Go ahead and just loop through, add them up, and we can do accelerator dot print number of parameters and params, right? That's it. Nothing crazy. And we can now build our data loader. So we have our mini batch size. If we're doing grade accumulation, then we're going to do the args per GPU batch size, right? So what's the batch size that we actually want per GPU, and divided by args.gradient accumulation steps, right? So if we want a batch size of 64, but we're going to do it in 4 chunks, then each mini batch size will be 16, right? So that's how I like doing it. And we need a simple collate function. Collate function will be very easy here. All we need to do is our tokens is going to be torch.stack, torch.tensor, b. We're going to grab the input IDs, just like we saved them in our data. And we'll make sure they're in d type equals torch.longTensor, so in 64s. And we'll just do that for b and batch. So we're going to loop through our batch and go ahead and grab them and then stack them together. And the reason we can just directly stack it here is because everything is the same 1024 length, right? So it's easy. So we can return input IDs is our input IDs. And that's it. Or sorry, not it'll be tokens, right? That's what I call it. Good. So our tokenized data is going to be, again, load from disk, and we'll do args.path to prepped data. Our train data loader is going to be standard data loader, tokenized data, and we're going to grab the train split, and our batch size will be the mini batch size. Our collate function will be just that collate function, and then our shuffle, right? We always want a random shuffle during training, so we can do that. And our test data loader will be exactly the same thing, so we can just copy it in. But this will be a test data loader, or let's call it eval data loader. We're going to grab the test split, but mini batch size is fine, and we don't really need to shuffle during evaluation, right? So we can get rid of that. And now we need our optimizer. We can do optimizer is going to be torch.optim.atom w model.parameters. LR is args.learning rate. I didn't do any fancy things like LoRa or anything here. We'll just keep it simple. Weight decay is args.weight decay, right? So standard optimizer, nothing new. We can also get a scheduler. I'll just copy this in. Right, scheduler. I think I set it up to use the cosine scheduler, so standard cosine scheduler with warm up, and we scale it up for the number of processes because if we have 6 GPUs, then the scheduler will step 6 times, so we need to just make sure we account for that. So there we go. So we have our scheduler. And our simple loss function. Well, there's really nothing different than mass language modeling, so it's just going to be nn.cross entropy loss. And reduction equals none. You'll see why later. So we're going to do cross entropy loss, but we're not going to average it up or anything. We'll do that ourselves afterwards, and there's a specific reason for that. So we'll see that play out in just a second. And so now we can prepare everything. We have our model, we have our optimizer, we have our train data loader, we have our eval data loader. We have our scheduler. It's going to be accelerator.prepare. Again, model, optimizer, train data loader, eval data loader, scheduler, just like that. And so we can now go ahead and start training. So train is true. Completed steps is 0. And our progress bar is going to be tqdm range completed steps args.num training steps. And then disable is not accelerator.is local main process, right? So we only print out the progress bar once. No need to do it for every single GPU that's running. And so we're good to go. That sets up everything we need, I believe. So we can now start training. So while train, we're going to do first accumulate steps is 0, and our accumulate loss is 0, because of course if we're doing gradient accumulation, we need to accumulate all that stuff up together so we can not visualize, but just plot our loss and stuff correctly, right, over the accumulation. And so we can do for batch in train data loader. We're going to do our input IDs. Input IDs is going to be batch input IDs dot to accelerator dot device. Put on the right stuff. And now here's basically what we've all been waiting for. We need to implement our random masking strategy. So it's going to be grab IDs, whatever. And now we're going to we need to first attend to all tokens. Remember, we have pad tokens on some of these samples, but those pad tokens matter. We need our model to be able to see and predict pad tokens, so we need to train on them. So we're going to have an attention mask where everything is attended to. So very simply, we're going to have batch size by sequence length. It's going to be input IDs.shape, and then our attention mask is going to be torch.ones batch size by sequence length. D type is torch.long, and device is going to be accelerator.device. So we're going to go ahead and just create ones, because again, we want everything to be attended to. So everything is 1, so it's always attended to. Also, if we didn't pass in anything, then it would default to this anyway, I think. But either way, we want everything to be attended to. So there's no zeros. Everything is 1. So our attention mask is attend to everything, mask or not. And that's important because this starts to pre-initialize that pad token, or in our case, the EOS token, such that in future steps, when you do supervised fine-tuning, it'll go ahead and actually predict those, so it knows when the sequence ends, right? How much of our masked canvas should it use to actually represent its answer? And now what we're going to do is the key step, random sample t to mask tokens. So we're going to do t is equal to torch.rand, and for every sample in the batch, right, so batch size, we're going to predict one number, and we're going to make sure it's on the accelerator.device. This will go ahead and just create basically something like this. Go right here. So let's say we have basically the sequences, token 1, token 2, token 3, token 4, and then another one, token 1, token 2, and maybe like a pad, whatever it may be. I'm going to go ahead and generate a random number between 0 and 1 for each one of these. Let's say I generate 0.2 and 0.6. And so that's what I just created here. And now what we're going to do is we want the 0.2 to apply to everything here and 0.6 to apply to everything here. So we're going to go ahead and just create 0.2, 0.2, 0.2, 0.2, 0.6, 0.6, 0.6, 0.6, right? Just go ahead and just repeat it essentially, or expand it, right? So we can do our, this is going to be this dot expand, and we're going to leave it as batch size here by sequence length. So that's what we just did. And we always want to make sure that something is masked. So 0 is not that helpful to us. So to deal with this, all we do is dot clamp, we just minimum it, right? Clamp min 1e minus like 5 or something. So it's never just 0, right? And so now that we have that, we can do our, and there's another reason for this. We're going to divide by t later, you'll see. So this makes sure we never divide by 0. And now we're going to do mask is equal to torch.bernoulli dot bool. So what is torch.Bernoulli? Torch.Bernoulli does exactly what you think. So we can do, let's just kind of show this out. So t is going, let's say we have a batch size by sequence length is equal to 2 by 4. And so we're going to do t is torch.rand. And let's import torch here. Import torch. Torch.rand. We're going to pass in batch size by 1. Print t. So let's see what that looks like. Python pretrained.py. So we generated two numbers here, right? 0.2 and 0.8. And then we did .expand batch size by sequence length, just like I mentioned. So now we've, print t. There we go. So now we've repeated that same number here. So we want to now, for every single one of these tokens along this dimension, if we predict a random number less than 0.1569, then it's selected to be masked. If it's greater, then it's not selected. And torch.Bernoulli, it's basically like flipping a weighted coin, right? A coin that has heads being likely to be 0.1569 and tails being, everything else. So we can do torch mask is going to be torch.Bernoulli t, and just make it a Boolean. And so we can now print out our mask. And we get this, right? Some things are selected to be masked, some things are not selected to be masked, and it's random every time. And we can make this maybe 16, and we can print out t as well. And so you can see it, right? So we have here, everything is 0.2774. So with about 27% likelihood, every token in this sequence will be selected to be masked, and we can see that happen. Same thing here. They're all kind of the same, so we can try two different numbers. These are now both about 70% here, 40 and 70. So we have stuff being masked here, stuff being masked here, so on and so forth. But we can see it's random masking, right? The proportion of things being masked is always random, and that's exactly what we just did here. That's our mask. And so now what we're going to do is our masked input IDs is going to be equal to input IDs dot masked fill mask tokenizer dot mask token ID. Go ahead and fill our input IDs with the mask token for all of those positions. And then our labels is going to be the input IDs dot masked fill mask, or everything that's not the mask, -100. So what does that exactly mean? Let's say we sampled this one and this one, these to be masked. So in the end, and let's just do maybe, let's say these got masked. So that means our data looks like this: mask T2, mask T4, and then we have mask T2, pad, right? That's our data. But I know what the correct answers are, right? I know what the answer is here and here, and I know what the answer is here. That would have been T1 and T3 and this T1 over here. But everything else, we don't need to compute the loss on. Just like in mass language modeling, we only compute the loss on the masked positions. So for our labels, we're going to replace these all with -100s, right, for the labels. And so that's all we've done here. We filled our labels, the input IDs, everywhere that it wasn't masked, they're -100, because cross entropy will automatically ignore the -100 index. So very simple. And so now let's go ahead and grab our logits. This will just be the output of the model. It's going to be our model. I'm going to pass in input IDs as masked input IDs. We have our attention mask is our attention mask, which even if we didn't pass it, wouldn't have mattered. And we're going to go ahead and just grab those logits, right? Because it returns a dictionary of all its outputs. We only care about the logit outputs, so there we go. And so now we have basically our outputs, and these outputs are going to be in the shape of batch by sequence length by number of characters, right? Number of characters. And so now let's go ahead and compute our loss. So first, num classes is going to be logits.shape -1, right? Because it's batched by sequence length by number of classes. We predict, the logit, not the probability, but the logit distribution over what token could it be. And then our loss is just going to be that loss function, right? Standard loss function. And it's going to be logits.reshape. We're going to flatten the batch size times sequence length dimensions, and it'll be num classes. And then our labels or we can just flatten it actually. We don't need to do a reshape. There we go. We now have our loss. And let's see if we can actually run this just to see what it looks like. So I'm going to grab the training script for it. So pretrained.sh. Yeah, that should work. So let me go here, new file, pretrain.sh, and this is just to load some of those arguments in. We'll do ModernBert base here, which is quite a bit smaller just for speed, and everything else should be fine. I believe I have to update this path again though, so let's grab you and put you right here. There. All right, so let's do loss, and then we can throw a break in here so we can see what's going on. So we can do bash prepare pretrain, or not prepare pretrain. We're going to just do bash pretrain.sh. Let's see if we have any bugs. It'll actually print out the loss twice, but that's fine. Yeah, so loaded the data, no problem there. And there we go. So it printed it out twice, and it should, oh yeah, I guess it's going to keep going, but we're going to exit here. That's fine. So you can see it prints out our loss, and it prints out a loss value for every single every single index, right? So because we flattened everything, so for every single token in our batch and sequence length, we have some loss value here. And so that's good to see here. And there's a little bit of a problem with our setup though. And it comes down to this. So we're going to do, let me double check here that I get this correct. The problem is that when we compute our loss, it's actually kind of unfair. The reason it's unfair is when we have more mass tokens, when t is higher, it's harder, right? It's more challenging for the model to predict something when t is higher. As opposed to if t was low and there's only a couple words missing, it's no problem. And so we just need to do a little bit of loss rebalancing here. And so what we're doing is essentially this. We're going to do loss is going to be loss.reshape, batch size by sequence length. Let's go ahead and do that. And so this just puts our data back. And then we're just going to divide by t. Because remember, as t gets bigger and bigger, this becomes a more challenging problem. And so we'll divide that specific sample by t. Right? And that's it. That's the big idea. As t gets bigger, we're going to scale the loss down. As t gets smaller, we're going to scale the loss up. And that's it. This just helps us deal with this issue of the loss balance. And now that we have that, we can do loss is loss.mean. This was also found in the paper, by the way. You can see that they divide by a t here, right? Because they want to make it fair. And then this is why we also didn't do the reduction here. Normally reduction is mean by default, but we did it right here just so we could do this loss scaling. And there we go. And so now we can do loss is equal to loss.args.gradient accumulation steps. Accumulate loss plus equals loss. And then we can do accelerator dot backward loss. There's a couple things to keep in mind here. Notice in my accelerator right here, I didn't provide the gradient accumulation steps. If you did, then it would already scale the loss on its own in the back end. But because I didn't put it there, then I have to scale it myself. But it doesn't really matter whichever way you do it. And so this goes ahead and computes our loss, and we can do accumulate steps plus equals 1. So we've done one accumulation step. Now we can do if accumulate steps is divisible by our args.gradient accumulation steps. So 0. So, you know, if we set our gradient accumulation steps to 4, then, well, every 4 steps, what we can do is actually update the model. So we can do accelerator dot clip grad norm standard stuff, right? So model dot parameters, go ahead and set it to args dot max grad norm, typically just 1.0. So go ahead and clip our gradients in case there's anything crazy in there. We can do optimizer dot step, and then we do our optimizer dot 0 grad. And we can do set to none equals true, right? Just for some efficiency. And we can also go ahead and update our scheduler. So scheduler.step. And that's it, right? That's basically our training. So now we can just go ahead and do a little bit of work. So we can do if completed steps, %args.logging steps is 0. So every completed step, basically. Go ahead and do accumulate loss is going to be accumulate loss.detach. Right? So we don't need that anymore. And we can do if accelerator dot state.num processes greater than 1 if we have more than one GPU running. Then we also need to do our accumulate loss is going to be torch.mean. And we just need to do accelerator.gather for metrics accumulate loss. So this is going to go ahead, grab our accumulate loss tensor from all the different GPUs, gather them into a single tensor, and then we're just going to take the average of them. So this is my average loss across all the devices that are training. And now we can do log is equal to train loss, accumulate loss, and then our learning rate, so we can take a look at it, is going to be the scheduler.get, get last LR? Yeah, 0. There we go, that's our log. And so then we'll have a logging string, and I'll just kind of paste these in because that's less interesting. But this will just print out how things are going, and we can write it to the progress bar, and then we can write it to weights and biases if that's what we're doing. During inference time, there is absolutely nothing different, obviously, right? During inference time, we do exactly the same thing. So we can just go ahead and copy paste everything that we have just done. Let's see here. If completed steps, I think this is, yeah, good. Yes, so during inference time, so if completed steps dot, args every evaluation number of steps, we're going to go ahead, throw the model into evaluation mode, create a dictionary store of val loss, loop the validation data, do exactly the same thing, attend to tokens, random sample, mask things out, compute logits, compute our loss, rescale the loss, store the loss in our thing, accumulate it, divide it by the number of losses, and there you go. Throw the model back into training mode. And then once we've done training, there's again really not a lot going on after that, so we can just, this is like the least interesting part to y'all, so we can just ignore it. We will go ahead and checkpoint the model every checkpoint steps. We'll go ahead and save the model. We'll go ahead and if we have more, if we've done enough steps, then go ahead and end training. Otherwise, go ahead and do completed steps plus equals 1. We've completed one full step, update the progress bar, and reset the accumulated loss for the next accumulation. And so this is, a very, very bare bones standard training script, nothing fancy. And so if we run this, we should see something. Of course, I'm not going to make y'all watch a training loop because who wants to do that? But we can go ahead and just make sure things are working as expected. Okay, looks like I have a bug. So I have accumulate steps plus equals 1. So let's do that. Accumulate steps. Let's see here. I have, did you mean accumulate step? Accumulate. Oh, I did accumulate. Wow. Accumulate. There we go. Okay, that's probably right. Let's see if everything else is working and if we're golden, and then we'll move on to supervised fine-tuning, which the training script will be identical actually. It doesn't change much. It's just all that changes is we have to make sure we don't mask the wrong things out. So you can see stuff's happening. It's running the inference loop now. So obviously no one wants to watch a training script. So let's work on the supervised fine-tuning, which again looks identical to what we've done here. And then after supervised fine-tuning, we'll write the actual inference script, right? So we'll see what the reverse process looks like. It'll just be easier to write that once we actually have the supervised fine-tuned model as well, just so we can write one generic inference script that can accept prompts or do completely unconditional generation. So to do this, we're going to need to prepare our SFT data, which again will look a lot like what we had just done. So we're going to do prepare SFT data.py, just like that. And again, we're going to have, most things will be about the same. So I'm going to copy in the arg parse at least, and then we'll start working on the SFT data. So there's all sorts of SFT data sets that you can pick from, especially on Hugging Face, but all over the place. The one I picked just because it's popular and easy is the Alpaca data set. So let me pull it up by Tatsu Lab. It's very simple. We have a input and we have a output. So that's all we want. We have our instruction and we have our output, and sometimes an instruction also has this extra input, so we'll go ahead and add that in if it's there. And then there's also kind of this full text version of it, but that's also fine. We can just do it this way. So we need to essentially do our chat template, which we know is pretty simple to set up, so we can go ahead and do that. So using these arguments are about the same as before, nothing new. So step one, we're going to do def prepare data args. And step one is going to be, just like before, context length is args.context length. Our path to save is args.path to save. Path to data store, path to data store. And then our cacher is going to be args.huggingface cache directory. And so we'll do our tokenizer is going to be the get tokenizer method that we wrote earlier, args.hf model name, grab the tokenizer for our specific model. Our data set is going to be the load data set. Feel free to change this to whatever you want. But this is the Tatsu Lab Alpaca. And this is pretty straightforward, essentially. So we have Tatsu Lab, Alpaca. Oh, and we need to grab the specific split. So we'll do split is train. We have our num procs is args.num workers. And then we have our cacher is, well, cacher, right? Nothing fancy. And so we have our first method, def apply chat template. This is going to take some query, some response. We'll set those up in a bit. And the chat template was exactly how we had it. We had tokenizer.getApply. We had the apply chat template. And it, well, did it exactly like this, right? We had the role, which was assistant, or user. And the user provides some content. And the content will be the query. And then similarly, we'll have the role, who's going to be the assistant. And then we'll have the content, and that'll be the response, right? Response. Now, of course, this is for a single turn. We could have also done a multi-turn setting, but that's not as simple. So we're not doing that here. And I don't think Lotto was ever trained on multi-turn, so I'm not exactly sure. We could look at that later. Tokenize is true, and add special tokens is also true. There we go. And we have our preprocess, def preprocess. This is going to be, we're going to take an example. And then like we saw, there's three columns, right? There's the instruction, the input, and the output, right? So we're going to grab exactly those. Our instruction is just going to be equal to example instruction. We have our input. It's going to be the example. Grab that input. And then we have our output is example output, just like that. And of course, we may not actually have an input. As you can see, a lot of these things don't have some kind of an input. The input is just some context, right? Like transform the following sentence into the passive voice. I bought a book. A book was bought by me. So this is kind of like the content that you want the question to look at. So the answer kind of is about that content. We don't always have an input, so we can do if len input greater than 0, so if there actually is an input, then we can do instruction is equal to instruction dot replace. And what we're going to do is get rid of the period. So you can see all of these instructions here. They may end with a period or something, whatever it may be. If there's a period, sometimes it's a question mark. I could have been better about this, but whatever, it's fine. We're going to replace it with just an empty string, just so it's not ending. And we're going to add a plus, add a colon with a space, and then we're going to add the input onto it. So we're just going to go ahead and do it this way. We could have also made this thing fancier, like the role, user, content, query, input, input if there is one, but this is fine. We're just going to make one single thing where the content is basically the instruction plus a colon plus that input information if it's there. And so then our tokenized is going to be our apply chat template on this instruction and our output, right? And we can then return input IDs is going to be our tokenized. And the other important one is the len is going to be the len tokenized. There we go. Good. So that's everything we needed. Now what we're going to do is go ahead and actually apply it, right? So we're going to do dataset is going to be equal to our dataset.remove columns text, right? Go ahead and do that. Go ahead and remove any extra things that we don't need. And then our dataset is going to be dataset.train test split. This is going to be the test size is going to be args.test split %, right? And the seed is going to be args.dataset split seed. There we go. And then our tokenized data is going to be dataset.map. We're going to apply this pre-process function that we just wrote. The number of processes is going to be args.numWorkers. And then we're going to remove columns, and we're going to remove, again, we're done with them, so we no longer need the instruction, we no longer need the input, and we no longer need the output columns. So let's go back to the data set and make sure we got everything. So we already got rid of this column because we don't need it. And now that we've tokenized everything, we no longer need these 3 columns either. We just have our tokenized data. So that's good. We now have our tokenized data. And here's one key idea. We have to do def keep within context. The thing here is that if one of my answers are longer than the context length that my model provides, then I have a bit of a problem, right? Like the answer's clipped off. We need to make sure both the question and the answer all fit within that context limit. So this is just a quick filter for there was a couple examples in this data set where the context length is the question answer pair was longer than the context length of 1024 that we're working with. So we can go ahead and filter those out. So we can do our tokenize, well, this is going to be first return example length less than or equal to context length. So let's just say true false. Is it less or is it greater? And that's why we went ahead and added this extra length parameter here just to make this easy. And we can do now tokenized data is equal to tokenized data dot filter, and we're going to go ahead and filter keep within context, and then proc is again args.numWorkers, and then we're going to do tokenized data is this our tokenized data dot remove columns, and we no longer need that length column anymore either. And so that's one more step that we needed to do. And now here is the last step that we need to do. We need to figure out which tokens are answers and which tokens are queries. Because remember again, during our diffusion modeling, basically randomly masking stuff out, we never want to mask the question, the prompt. We only want to randomly mask answer tokens. So I just need a 0-1 mask telling me, is it an answer token or is it not an answer token? Now, if you remember, our data was set up like this. So it was essentially, we have a EOS token, and let's actually go back here to our tokenizer to see what this looked like. So yeah, this is perfect. So we're gonna do, let's look at this one right here. Because this is basically what we did, right? We took some messages that had some content and we encoded them. So let's just decode it and take a look and see what we had here. So if we do Python tokenizer.py, you'll see we have a beginning of sentence, start ID, end ID, user, end ID. What is a capital? End of turn. Then we have a start ID, assistant, end ID. Then the question begins. And here's the thing. Everything before this end ID, basically this end ID and earlier, we want to keep from masking, right? This is basically our input. What we want our model to mask is everything afterwards. In this case, it's just Paris, but whatever. So what we want to do is find, we have one end ID, two end ID. So let's find the second end ID. Everything at that index and earlier will be we don't want to mask out, and then everything afterwards is fine to mask out. So let's just go ahead and do that, and that's pretty straightforward. So the way we can do that is we can do prepare, prepare SFT data. Or write another method, def get answer mask. We're going to pass it an example, so we'll do it one at a time. Tokenize is going to be example input IDs. And what we're going to do is our query mask, empty list right now. We're going to do occurrence is 0, because we're going to be looking for the second occurrence of end ID. So there you go, our occurrence is currently 0. And is answer is false. And we're going to do for t in tokenized. Oh, my bad. Tokenized. We're going to do a quick check. It's going to be t equal tokenizer dot convert tokens to ID, and we're going to do the end ID, right? So, end underscore ID. There we go. So go ahead and see, is this t equal to the whatever token ID represents this one, end ID? So that's my sanity check, right there. If not, is answer. So we're not, we haven't started yet. Then it's going to be query mask dot append 0. Right, so go ahead and append 0, as we're still not in the answer portion. We haven't really flipped that flag yet. You'll see that in a second. Else, query mask dot append 1. So once we have this flag is answer, at the beginning it's false. Once it's true, it's always true, right? Once the answer tokens begin, everything else is answer tokens, so it's fine. So we start with that, just a quick check. But we need to flip that token based on this condition. So we're going to do if check. So if t is equal to the end ID, well, then we have to do a quick check here. If occurrence is 0, because remember, there's 2 of them, so there's the 0th one and the first one. If it's 0, well, then we're not at the second one yet. So then all we need to do is occurrence plus equals 1. Else is answer is true. Go ahead and toggle it. So the second occurrence, once we do another plus equals 1, so basically the second time, it's going to go ahead and start doing is answer. And then once this answer is set to true, it'll keep on appending 1s over and over again to our query mask. And so then we can do example. Query mask is our query mask. And we can return example. So this simply just gives me a 0-1 mask of which tokens are query tokens and which tokens are answer tokens. That's it. So we can do tokenized data is tokenized data dot map, and we can do get answer mask num proc is args dot num workers, and lastly we'll do tokenized data dot save to disk path to save. Very simple, right? Nothing fancy. And I won't even bother showing you the dataset because it won't look any different. Basically, it's a dataset with 2 columns, one column with input IDs, and the second column is for every single one of those input IDs. Was it a 0? It's not a query, or yes, it is a query, right? And we can use that mask for training purposes. So let's go ahead and write our training script for SFT. So now we're going to do, let's see, I'm going to call this SFT trainer.py. And honestly, this training script is 99% identical to the other one. So what this is going to look like is this. I'm going to copy everything except for the one part that changes. So everything here is identical. Okay, actually I need to write a data util. Let's do that real quick. I wrote that right here. So let's actually do that real quick because that's important. So we're going to do data utils.py. We're going to write import torch, import or from datasets, import load from disk. We have from torch.utils.data, import data loader. We have from tqdm, import tqdm, whatever it may be. So the reason we have to write a better collator, so we're going to do def SFT collator. The reason we have to do this is because every single sample now is a different length. So where we earlier in our pre-training, right here, when we just concatenated everything together, where's that collate function? Right here. We just concatenated, we stacked everything together because every sample was exactly the same length, no problem. Everything is now not the same length, so we need to make sure we actually deal with that. So what we're going to do is this. So let's go back to data utils, collator. We also have from Tokenizer, right? Tokenizer, get or import get Tokenizer. Very simple. And this collate function will be for a specific model name, right? So a specific model. In this case, we're doing answer.ai, again, ModernBert base. Good. So our tokenizer is going to be get tokenizer. Model name is get tokenizer. There we go. And we have our EOS token is going to be our tokenizer.EOS token. So let's kind of remind ourselves what we have right now. Our data right now is like this. We have some prompt tokens. Let's say we have P1, P2, P3, and then we have some answer tokens. Answer 1, answer 2, answer 3, answer 4. But a different sample could look like this. It could be prompt 1, prompt 2, prompt 3, prompt 4, and then answer 1, answer 2, answer 3, answer 4, answer 5. Right? That could be fair. Which means we need to add some pad tokens, like we always do, to the end of this one. The only difference is that we always want to attend to these pad tokens as well, right? That's a key idea. So let's go ahead and just add these pad tokens on, but the pad tokens are important and they'll always be there. So we're going to do def collate function batch, and it's going to be inputs. It's going to be torch.tensor b input IDs for b in batch. These are all of my inputs just as a list, and then our query masks. Because again, remember, I currently have a mask telling me that these things are things you don't want to do any kind of masking on, and then these things are the things that we do want to do masking on. But if I add extra pad tokens, these are fair game. We want to train on them, which means these are also fair to mask. So we need to extend our mask as well in the same way. So our query masks is also going to be torch.tensor b query mask for b in batch, just like that. And so our inputs is going to be equal to torch.nn.utils.rnn.pad sequence, just like we always do. We're going to go ahead and pad them. We're going to pad these inputs with a padding value of the EOS token, and then batch first is true, just like always. And then our query mask, exactly the same thing, torch.nn.utils.rnn.pad sequence. And again, we're going to pad our query masks. And the padding value, in this case, padding value, will equal to 1, because 1 is these are candidates to be masked. So we're just going to essentially just keep extending those 1s on. So there we go, 1. And again, batch first is true. And we can then return our input IDs, which will be our inputs, and then our query mask, which will be our query masks. And we can return this collate function, so we can use it as a data collator. So we can actually test this real quick. Let's just paste this in. Go ahead and grab our data set, load it in, and then just test this out. So let's print out the, let's do a batch size of 2. Python data utils.py. Could not infer the D type of generator. Let's go ahead and give this a quick test here. So it's print batch right here. Okay, so we have our input IDs. It's just a list as far as I can tell. We have a second input IDs right here. Input IDs. dtype is torch.long. That's what it should be. So let's just, oh, whoops. This should have been right there. Looks like that was the issue. All right. Padding value must be a float, not a string. So this is going to be EOS token. Let's check this again. ID. There we go. Right, so we have our input tokens. The longer thing, or the shorter thing, has been padded, however, and we have our masks here, right? So we can see that all of these tokens were question tokens. We cannot mask them, but all of these tokens are answer tokens. These we can mask, and that's why it's important to just have this extra piece here so we can handle that in our setup. So with this out of the way, we can now go back to the SFT trainer, right? SFT trainers, again, 99% identical code to what we had done earlier. You can see right here in our data loader, we go ahead and load that SFT collator that we just wrote, so no problem. And what we can do now is essentially do the one sanity check before everything else is identical. So what this means is we have our, let's see here. We have, from our batch, we grab both input IDs. It's going to be batch input IDs, right? .to accelerator.device. And then our query mask, it's going to be batch query mask, again, .to accelerator.device. And so again, just like before, batch size by sequence length is equal to input IDs dot shape. And our attention mask, because we want to attend to everything, pad tokens included, torch.once is going to be batch size by sequence length. And our do dtype, again, is going to be torch.long, that's what it expects, and device is accelerator.device. Make sure it's on the right GPU. And so now, just like before, again, we're going to random sample some t. So t is going to be torch.rand batch size 1 device is accelerator.device dot expand, right? So we can repeat it for every single time step. Batch size by sequence length and dot clamp min 1e minus 5, right? That's gonna go ahead. It's just so we don't have the divide by 0 error. All right, and then the last thing is our mask. Our mask is going to be equal to torch.bernoulli t. And so what we've done is, again, for every single one of these samples, we've predicted 0 or 1. Should this one be masked? Should this one be masked? Should this one be masked? Dot, dot, dot. And we've basically predicted a 0, 1 vector of what things should be masked, what things shouldn't be masked. But we want to make sure that these tokens here are always 0, because we don't really want to mask them. Why would we? We only want to mask the stuff after them. And that's why we have that extra mask. So what we're going to do is just take this mask that we created here and multiply it. So it's going to always set these to 0 as don't mask, but these things will be 0 or 1 depending on how they were randomly sampled, right? So it's very simple like that. So we can do, just very simply, our mask is actually going to be equal to mask times query mask. And then mask is equal to mask dot bool. And that's the only code change we have from what we had before to what we have now. We just essentially just have well, actually it's one of the two changes. We still have one more change that we need to do, but that's the main code change that we had, right? We're essentially including this query mask. So now let's keep going. Everything after this is identical, so we can go ahead and paste that in. So stuff that's the same, I won't make you watch me re-implement it. Again, go ahead, fill our tokens, right? Fill our input IDs with this mask, and this mask we've ensured that any token that is a question token is set to 0 or set to false, right? 0 becomes false, and as long as it's false, then it won't ever be masked. So our input query tokens are never masked, only the answer tokens are. Go ahead and fill the input IDs, the labels with -100, the things that we aren't masking, so that's for our loss. Go ahead and compute logits, go ahead and compute our loss in the same way. We still are not reducing anything. Now, there's one other key thing that we have to keep in mind, different answers have different lengths. So we will also scale by that too. Longer answers could be tougher. Shorter answers could be easier. So we want to scale by that as well. And you get to see that right here as well. They divide by both t and by L prime, right? L prime is the sequence length of basically the answer that we care about, right? So let's go ahead and do exactly that. So our answer lengths is going to be our query mask dot sum dim equals 1, right, along the second dimension, and keep dim equals true. So all we've done is we've basically taken this 0, 1 vector and we've added it together and we just produced a number 1, 2, 3, 4, 5, 6. So we produced 6 because the length of the answers plus padding was 6 here. And that's it, right? Nothing fancy. We'd do exactly the same thing here. Here it'd be 1, 2, 3, 4, 5. So here it would have been 5. So it's whatever the length of the answers are. And so again, we're going to do answer. Our loss is going to be loss divided by answer length. We're going to rescale by that as well. And so now we're going to do loss is equal to loss.sum dim equals 1. We're going to add up our per token loss across each sample and then do the average of it after that. And that goes ahead and basically just does exactly as defined, right? So nothing fancy. That's exactly what you see right here, right? Just add them up and then divide. That's what we did. Good. So now that we have done all of that, everything else in this code is identical to earlier, right? Nothing new has changed. So we can go ahead and just paste it in, right? So accumulate, here we go. Right, nothing new. Everything in the code is identical, so I won't even bother going over it. So as you can see, SFT, training for question answering versus training for pre-training, is basically the same, just that little bit of a code change to make sure that we're only masking question tokens. So our model now needs to learn, can you unmask answer tokens given these input question tokens that are always there? They never disappear. And so now that we've all done that, now for the actual fun part, how do we inference this model? And inferencing this model is relatively straightforward. So let's go ahead and give this a try. We're going to do new file, inference.py. And we'll spend a little bit of effort making the inference look nice so you can kind of get that view. So again, we're going, this is our goal, bash, we're going to do bash inference.sh just to kind of give a reminder what our goal is here. We'll be using a package called rich that lets you do stuff like this in the terminal, which is kind of cool. Again, shout out to the repositories that I cited at the beginning as kind of a reference to how to do this, because I've never used rich before, but that was fun. So here we go. We now have all of that stuff. So this is basically what we're going to be building, right? How do you do all this stuff? Alrighty then. So we're going to need a couple things. Import logging, import argparse so we can inference from terminal, from transformers, import auto model for masked LM. That's the the model that we made. We're going to need torch, and we're going to need a couple things from rich. From rich.live, import live. It's basically like how we control the terminal. From rich.console, import our console, and then just a couple things that we're going to need, like from rich.progress, import our progress, bar column, text column, time elapsed column, and time remaining column. And we're going to need from rich.text, import text, and we're going to lastly need our from Tokenizer, import get our get Tokenizer, and our from safe tensors dot torch import load file. And so in here, all right. Oh, my pencil's being weird. All right, there we go. All right, so what we're doing here is I am going to grab you, copy, and paste it right here. I'll just take a second. But this working directory basically has some of those checkpoints that I've already created. The first set of checkpoints is from pre-training, and then the second set of checkpoints is from fine-tuning on the Alpaca dataset, right? So we have the pre-training on all that data. This is a LDM. This is a large model, so I trained the whatever it is, basically the large ModernBert architecture with about 400 million parameters. But I have a feeling it's a little undertrained. I could have probably trained it for like a week or something like that, but that's all right. I didn't want to wait that long. Load model and tokenizer. Let's go ahead and do that. So we have the path to weights, right? The model.safetensors. We have our HF model name, and device is CUDA, right? That's typically how we want to inference it. And we're first going to do our tokenizer is the get tokenizer. There we go. And we'll grab it for that HF model name. And there we go. And then we have our model is going to be the auto model for mass language modeling dot from pretrained. And we're going to do our HF model name device map equals device. Now this is going to go ahead and load the actual original Roberta model, or the ModernBert model, whatever you're using. I want to load my own weights into it, but I first have to do model.resize token embeddings, and we'll do len tokenizer. We want to make sure we actually resize it, right? I should have probably copied it through. Oh well, we'll see what happens. If it breaks, I'll fix it. Okay, so we're going to go ahead and resize our model, and now that we have that, we can do our state dict is going to be the load file from safetensors on our path to weights. We can then do model.load state dict, and we're going to load our state dict, and we can do strict equals false, right? And we can do model.tie weights. There we go. And model.eval. So that goes ahead and sets everything up as needed for our training purposes, or for inference purposes. So we're going to return our model tokenizer. Good. And so we're going to have two types of inferencing. Type 1 is we will have a unconditional version where we don't give a question, and then we have our conditional version where we do give a question. So we're going to do def prepare unconditional tokens for inference, right? Inference. And it'll be sequence len, mask token ID, and CUDA, right? Device equals CUDA. Okay, I feel like this might have been a small mistake to copy it through. Okay, I think it ended. Okay, good. It's done. All right, let's keep going. So our input tokens is going to be equal to torch.full batch size of 1 by sequence len, whatever we pick, mass token ID, dtype is torch.long, device equals device. Because again, remember, when we're inferencing, we start with all mass tokens and we iteratively denoise it. And we'll see what that looks like in a bit. Our mask is going to be just torch.ones, 1 sequence len. Again, dtype is equal to torch.bool. So this is our mask. Right now, everything is just 1, so everything is masked. So it's just our flag to keep track of that. And our attention mask is very simply just all ones, right? So torch.ones, 1 by sequence len. We'll have our dtype is torch.long, and device equals device. And now we can return our input tokens, mask, and attention mask. There we go. So that goes ahead and prepares all of our tokens for the purposes of inferencing, right? Unconditional. So there will be no input question. It's just a unconditional generation. Similarly, we need to prepare conditional tokens for inference, right? So we're going to do def prepare conditional tokens for inference. So now we have, again, sequence len, tokenizer, prompt, device equals CUDA. And this will be, again, our chat template is going to be, just like from before, we're going to have a role, who will be the user right at the beginning, and then we'll have the content, which will be that prompt that we provide, whatever it may be. That should be a comma right there. And we can now do tokenized. It's going to be our tokenizer dot apply chat template. Chat template tokenize equals true, add special tokens is again true, and then add generation prompt equals true. So add generation prompt is going to make sure it does the role, user, and then our question, but then it's also going to start the start assistant token essentially, and then from there it will start generating. So we now have our tokenized stuff, and so we can now do very simply our prompt tokens is going to be torch.tensor tokenized, and we'll make sure it's on the right device. And so now we have input tokens, mask, and attention mask is going to be equal to prepare because everything after this is the same, right? So we can do sequence len tokenized tokenizer.mask token ID and device, right? The everything here to set up the input tokens and the mask and the all of that is the same, right? Nothing else changes. So we can just use that directly. All we're going to do now, though, remember this input tokens is just going to generate a bunch of mask tokens, and then our mask will all be ones. But of course, in our case, we want to make sure our input tokens, the zero, we're setting this up to only be able to inference one sample at a time. You could also do batch sampling, but I didn't bother. Len prompt tokens is going to be equal to prompt tokens, because right now input tokens is all mask tokens. But of course, during inference time, if I provide a condition, I want to replace the first prompt tokens worth of tokens with our actual prompt tokens, right? So it can see that. So now we have prompt tokens and like that start of assistant, and we have a bunch of mask tokens that are ready to be essentially unmasked, right? To be inferenced, to be denoised. And then our mask, similarly, mask len prompt tokens is false, right? So everything here, basically the first prompt tokens, again, they're not mask tokens anymore, they're prompt tokens. So there's no reason to do anything with them, so false. And we can now return input tokens, mask, and attention mask. Attention mask is always one, that doesn't matter. And so let's go ahead and start writing our inference method. So at torch.noGrad def inference, we'll pass in input tokens, mask, attention mask, num steps. So this is a inference time hyperparameter. How many steps of inference do you want to do? And we will have our device is CUDA, and our prompt is none, and show mask is true, just so we can see it happen. And so for step one, we need our console. And this is kind of just me digging through the documentation for Rich. So there's nothing fancy here. Highlight is false. Just go ahead and create a console in which we will actually do this stuff. And the way it works for Rich is we can do with progress. So this is going to be a progress bar. And inside it, we're going to place all the stuff that we want. So the first one's going to be a text column, inside which we're going to have a progress.des. Let me fix that. Inside which we're going to have a progress.description, and then we're going to have here task.description. Okay, and then we have let's keep that there. And then we have a bar column, just so we have a separation basically. And then we're going to have another progress.percentage. You can honestly skip ahead. This is like the not interesting part. Percentage is just to make it format and look fun. But we can make a percentage here, and we can make it make sure it's always 3 decimal places or something like that. So there you go. Nice. And then we have our time elapsed column, time remaining column, console equals, well, this is the console we want to print it to, and transient is true, it should just stay there. So with all of this as progress, and where did I get this? I basically just found an example online and used it, right, from their documentation. So this just creates that progress bar that we saw earlier. So that's fine, not a big deal. And so we're going to do task is progress.add task. This will just throw a thing in there for generating total equals num steps. So however many steps we want to generate for, it's a hyperparameter. We'll see how that affects things in a bit. And we'll do times, and this is the important part. This is the most important part of our entire inference script. Right now, we have essentially trained our model to go to denoise anything from 0% to 100% masked, right? And of course, we're starting with 100% mask. And so when we inference, we start at 100%, right? So 1, everything was masked. And then we're going to denoise it to what if it was 90% masked, 80% masked, 70% masked. And this would assume we had 10 steps, right? Going from 1 to 9 to 8 to 7. But what if we wanted 100 steps? Then we had gone to 1 to 0.99, to 0.98, to 0.97. Because these are essentially the different noise levels, or essentially the different mask levels that we can have. And how many we want to do is completely up to us. And it's most likely that the more you have, the more granular the model can be. It has more opportunities to update itself. So what we're going to do is our times is going to be torch.linspace from 1 to 0, num steps plus 1, so we have it inclusive, and device equals device. So those are our times. We're going to do width live, refresh per second is 5, whatever, and console equals console as live. We're going to do for ts in zip times there to 1, or there to everything but the last thing. So t will be everything but the last thing, and then the s will be times everything but the first thing, because again, remember, we want to go from, let's just create a list of t's here real quick. So we have essentially 1, 0.9, 0.8, 0.7, 0.6. So I want to go from 1 to 0.9, 1 to 0.9 to 0.8, 0.8 to 0.7. So I just set it up as a list of everything but the last thing for t, which is my starting point. So it'll be 1, everything but the last item in the list. And then s is going to be everything but the first item in the list. So my t's will be like 1, 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1. And then my s will be 0.9, 0.8, 0.7, ... 0. So it's just me going from 1 to 0.9, 0.9 to 0.8, 0.8 to 0.7, rinse and repeat, right? So there we go. We're just looping through all of that. And that's why I have this extra +1 here, right? So the indexing works out fine. Our logits is equal to model input tokens. Attention mask is attention mask, and we're going to grab those logits. So this is me predicting. Where is the... I might have forgotten... I think we're good. Yeah, I think we're good. I should put up here our tokenizer, and actually, yeah, it should be right here. So we have our model tokenizer is equal to... Actually, you know what? It's fine. It's fine. So yeah, this is actually bad coding. I have model not defined here. That's because I will define it, or if name is main. Let's just paste the rest of this in just so it's clear what's going on. There we go. And this should be load model and tokenizer. There we go. Load model and tokenizer. So there we go. So in my if name equals main, right, in my script, I will load the paths to the model, prompt the sequence length, the number of steps, the we're not doing strategy today, just to keep this a little bit simpler. We'll have our model name, and this is going to be our, that's fine, I'll set it in the bash script, but that's fine. And then the device. And so we're going to go ahead and load those arguments, load our model in Tokenizer. If prompt is none, so if we don't pass in a prompt, then we're doing unconditional. If we do pass in a prompt, then we have conditional, and we're going to go ahead and inference our model, right? So there we go. So that's why it's bad coding. I should have defined the model in here so it actually exists inside the function, but that's fine. We'll just use closures and it's no problem. So now that we have all of that, we have our logits, our probs. It's going to be equal to torch.softmax logits mask dim equals -1. So what have we done here? We predicted some logits for each things. Now the only things we really want to predict something for are the things that are masked, right? Because, for example, if you pass in a prompt and then if you pass in a prompt and want an answer, we only want to unmask, or we only really care about unmasking the answer masks, right? In the answer positions. There's no point of predicting logits for the things that were already unmasked. So that's why we don't really care about it, right? So we can ignore that. So we're just filtering out for things that were specifically masked, and that's how we do it. And so then we can do our input tokens in those masked positions is going to be equal to, and we're just going to simply sample torch.multinomial probs num samples is 1 dot squeeze -1. So all we're doing is we're going to go ahead and these probabilities, it gives us basically a probability vector, right? We have for every single word, every single position, the probability vector. What could that word possibly be in that masked position? And I go ahead and multinomial sample them. In the original implementation for Lada, they use Gumball Max just for efficiency purposes, but this is fine. We can keep it simple here today. So yeah, we've gone ahead and randomly sampled one of those tokens from all the possibilities that it could be with that distribution, and go ahead and fill it in here. And this is essentially that first step of demasking. If we have some prompt, so we'll have some prompt tokens, and then we had some mask tokens, mask, 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 right? We have some mask tokens. And what we've done is we've gone ahead and predicted the most likely token. So what's the most likely token in each of these positions? A4, A5. And of course the prompt tokens stay the prompt tokens because these are not to be masked. So that's why we have that mask token earlier saying that these tokens are not masked, but these tokens are masked, just so I know, right? And that's the mask token we're doing. We go ahead and predict logits for each one of these things. We really only care about the logits for the things that were masked, thus that's why we're filtering them out. And then we use multinomial sampling to randomly sample from that distribution of logits what is the thing that we should have at these positions. And now is the key part. This is at time step t, we're going to some time step s. So now when we go, or some noise step s. So when we're at noise step s, what is the probability that if something was masked at t, that it'll be remasked at noise step s? And this is exactly the formulation we came up with at the very beginning. S over t is that probability. S over t is the probability that if this position here was masked at this noise step t, then with probability s over t, it will be remasked again in the next noise step. And this is how we keep everything consistent for our distributions. So let's go ahead and do exactly that. We're going to do remask probs is going to be torch.rand like mask. So it's uniform, and it's going to be dtype is equal to, just to make it certain, I think it already is, float, and device equals device. So just go ahead and generate some random noise in the shape of our mask, right? Just go ahead and generate some random noise. And then what we're going to check is remask probs is equal to remask probs less than s divided by t. So all I've done is I've generated some noise, again, for every single time step here. And then I'm just checking, is that noise less than s over t, right? Less than s over t. If it is less than s over t, then those time steps will be remasked. So let's say this one was less than s over t, and this was less than s over t, and this was less than s over t. Then these will be reconverted back into mass tokens, but everything else stays. And these will stay obviously by default because they won't go anywhere. They're prompt tokens, which means we have to do two things. We have to repopulate these positions with mass tokens, and because these two were not selected to be masked anymore, these will become 0. So whatever is not selected to be masked or remasked again will always be in your final answer, right? So they're basically kept around until the end. And so let's go ahead and do that. So we're going to do first mask is equal to mask and remask probs, right? So only replace our mask, only replace if our mask token was previously true and again true, right? So if something is false, if something's not selected to be remasked, then it gets set to 0, right? So that's 0. But if it's 1 and then selected to be remasked again, then it's 1 and 1 or true and true, and then that's just true, right? So mask and remask probs. And then we do input tokens at those mask positions is again tokenizer.mask token ID. There we go. And there's actually two different implementations they provide on the in the paper. So the first one is just random masking, which is the original implementation. They also try another method for low confidence masking. So instead of just randomly masking by s over t, filter out the lowest confidence tokens, like the things where the probability distribution wasn't very confident. So closer to uniform is essentially low confidence. And then only remask those with this s over t. You can look in my Git repo for that implementation. It's very simple. I just don't want to make this more complicated than it needs to be. And we can do if show mask decoded tokens is equal to tokenizer.convert IDs to tokens. And then we'll grab input tokens. And because there's a batch dimension, we can just index that out. So there we go. Those are our decoder tokens, and we've converted them to actual tokens, so they're letters, right? And we're going to clean this up. We're going to do cleaned tokens as an empty list, and we're going to do for token decoded tokens, because what this returns is just a list of all the different tokens, right? Just a list of them. So we're going to loop through them, and we're going to do if token is equal to tokenizer dot mask token, because we want to show the mask by default. We'll do clean tokens dot append token. Otherwise, or elif, token in tokenizer dot all special tokens. So everything else, pad tokens, and actually that's really the only other thing we have. We could visualize the pad tokens if we want, but that's fine. Let's just get rid of them. We'll just continue. We won't keep them. Otherwise, else, we can do cleaned tokens dot append token. So that's why I did this check first, just to make sure if it's a mask token, go ahead and store it. If it's, and mask tokens also in all special tokens, but at that point, this line is already cleared. So anything that isn't mask token, we'll go ahead and ignore them. Otherwise, go ahead and add them in and we're good to go. And so we need the final string. So decoded after is tokenizer.convert tokens to string cleaned tokens. And there we go. That's it for showing the mask. Else, decoded after is just tokenizer dot just standard batch decode input tokens skip special tokens is true, right? Just go ahead and just only print the actual sentence and ignore everything else, but that's not very helpful to see what's going on. And we're going to do if prompt is none. We're going to do something here. Format text is going to be format display for unconditional. And we're going to do decoded after. So we need to actually print this to terminal, and we have to use rich to do that to make it look nice. So let's go ahead and write two different print functions right here. So I'm just going to paste them in just to keep it simple. So the first one is essentially if there's a question answer, output is text. We're going to have user. We'll have the user text, that basically the question. We'll have the assistant text, and that's it. If it's unconditional, then it's just unconditional generation and the generated text, and that's it. So it's as simple as that. And we also have this simple, let me just throw this in here real quick. This is just some string formatting just to make it look nice. There's no scientific value to it, so I'm just going to put it right there. It's just to replace, it's just to clean up some of the text, because we no longer need user and assistant in our string anymore because I'm already printing out user and assistant right here, right? So there's no need to do any of that. Okay, good. So now that we have all of that, this is going to format text. Else, if we do have a prompt, then again, assistant text is going to be decoded after dot replace prompt. We're going to go ahead and replace the entire prompt with that because we don't need it anymore, and just strip any extra lines. Basically, I only want the answer, right? The answer from the assistant. I don't need the question here because I've already printed the question earlier. And assistant text is going to be clean text assistant text, and format text is going to be format display for QA, right? It's going to be on our prompt and the assistant text. There you go. And so we can now do live.update format text and progress.update task advance equals 1. That's basically a progress bar. And it's as simple as that, right? So nothing really fancy here. The key algorithm that I want you to make sure you understand is this right here, right? This is our remasking probability. Basically, we predict tokens for everything, but with probability S over T, if something was a mass token before, it can become a mass token again. And so we remask them and then just repeat it over and over again until we get to 0. And once we're at 0, then everything's predicted and we're done. So we can, again, I'll just do it in the Language Diffusion model, the original one that I made. So I made a script right here. Just do it here because I know it works. And has these right there. So I already have the path to the model and everything. So basically what I need to provide is my safe tensors, the sequence length. So the sequence length, remember, I trained up to 1024. And I can set the sequence length to technically anything I want, but 1024, because that's what it's been trained to do. But you kind of have to consider, like, if I'm asking a question like this, how much space do I need to answer it, right? If it's a really quick question, then there's really nothing to do. If it's a long question, then we might need more space. So I just set it to 512. And let's just keep this interesting. So what we're going to do is, again, the bash inference. So this is me asking the model, what is artificial intelligence, right? And so like we've seen a couple times already, we're essentially going to, and you can see those mass tokens are becoming pad tokens. That's why we're not printing them out anymore. But as we do that, it's essentially learning to generate our answer, just not autoregressively, which is a really, really cool property for these language diffusion models. And it learns that this is the amount of context I think I need to answer this question. It doesn't need to use anymore because it already learned to predict pad tokens because it can generate variable length sequences based on what it wants. If I ask it the same question multiple times, we'll expect to get multiple answers every single time, right? Different answers, because it's very stochastic, very probabilistic, just like diffusion, right? Just like diffusion. But the answers it gives you are pretty good. And this is, again, a pretty lightly trained model on that Alpaca data set, which was also very lightly trained, and it was lightly pre-trained on that big data set, only about a day or two, rather than a week or so that I should have done. So you can see it gave two completely different answers of different lengths, right? All right. So that's one thing. Let's see what happens if we change the num steps to like 5. If we only had 5 diffusion steps. These seem like pretty reasonable answers, right? Artificial intelligence is the science of developing a computer or software to perform certain tasks such as speech and voice recognition, content delivery, problem solving, natural language processing. Personal AI, which is a part of AI, refers to any type of automated task system that uses rule-based logic, such as customer service or predictive analytics, ... And this also seems like a pretty good answer. Science combining traditional calculations and calculations, abstract and strategic behavior. Sure, why not? I believe you. But let's see what happens when we reduce the number of steps significantly. Do we get a good answer? Not bad. Right? This actually seems like a pretty reasonable answer. And so this is basically a hyperparameter. See how quickly I got that answer? In generative models, like autoregressive models, we'd have to generate this one token at a time. I got it instantly. And this still seems like a reasonable answer even with 5 steps. Let's see if we do 2 steps. Conditional ones are a little bit easier, right? Because it has some text to go onto. And so you get this entire generated answer immediately. But we can see it starts to fall apart a little bit, so you can see it becomes AI official is AI is a intelligence of which of type of machine and involving scientific. So it's getting ballpark, but the language is not as good. It hasn't had more opportunity to basically remask and repredict, remask and repredict. Because if you look at S over T, when it's like large, for example, when we're doing S over T here, 1 divided by, we're basically doing 0.9 divided by 1, 0.8 divided by 0.9, 0.7, that's basically the same value going down all the way. And so we're actually remasking the majority of the data every iteration until we get to the end, right? When we have like, at here you'll have 0.1 over 0.2. That means even at the last step, we're masking out half of the things. And then at the last step it's 0, right? Because 0 over 0.1 is just 0. So that's one key idea. We can try asking it other things, so I don't know how well it's going to work. I don't know. What should I ask it? Tell me about neural networks. And let's let it answer for 1024 steps this time, right? So we're going to give it more opportunities to basically correct itself as it's masking. So you can see it's basically inference time compute. Just like diffusion, the more steps you take up to, the more steps you use, the longer it's just going to take to answer. Right? The longer it's going to take to just process itself. Just like diffusion, you have to wait 1,000 steps. The only difference is we get to now pick how long we're willing to wait based on the quality of answer that you want, which is kind of a cool inference time operation or decision that you get to make on your own. So yeah, we can start to see neural, let's give this a few more seconds. So we get a very long answer here, which is kind of cool. Let's scroll up. Neural networks are advanced forms of artificial neural networks, which were originally known as neural networks. The step is to build computers that are using learning models or of unsupervised experience to train machines and artificial intelligence. These networks are a group of nodes with mathematical inputs such as filters and nodes with numerical data or outputs. This is obviously not the best, but it's getting something that's kind of in the ballpark. Let's try something maybe a little bit different. I want to hear a story about a dog at the park. Let's see how it does now. I'm just messing with it. I haven't really tested this model on like interesting tasks because it's just a fun model for the most part. But again, as you can see, there's kind of cool opportunities here of what it can and can't do. It's mostly this. The fact that we're breaking the autoregressive nature of it is what interests me the most about this architecture. Because in the end, when humans think, it's not like we think sequentially. We think kind of as ideas that kind of all mesh together. And this is kind of reproducing a little bit of that, right? So you can see, oh, nice, we got a once upon a time. So it's an official story now. There was a loyal and mischievous pup who could do wonders with exercise, but was content to spend a rest in his paw. One day the dog watches the trees filled with leaves come jogging through the park. Doesn't make any sense, right? But maybe to a dog this would. So that's the the fact that walking was better for him than running. That's great. Okay, so that's basically the end of this video. Language diffusion models are awesome. I think there's a lot of cool research opportunity here, especially for a lot of non-text things, but require discrete supervision, or discrete modeling, because text is discrete. So hopefully this all was cool, and I will see y'all in the next one.